Hello everybody. I welcome you all to NCAS geology class. In last two classes I have discussed about the age of the earth, particularly the ancient methods of determination of age of the earth and the modern method of determination of the age of the earth through use of the radioactive elements, the parent element and their daughter products. I have already discussed the formula by which we can calculate the age. Now I provide the data about the half-life period of some of the elements which undergo decay and help in the finding the age of the rocks from the presence of daughter elements and parent elements in the rock specimens. So let us discuss the half-life periods. Uranium-238 converts to Pb-206 through alpha and beta radiations, and its half-life period is about 4.5 into 10 to the 9 years. And uranium Pb, these elements are found in common minerals such as zircon, pitchblende, uraninite. So these are the minerals in which we find these elements. Similarly, uranium-35 produces stable Pb-207 and its decay constant, this is the decay constant, and its half-life period is 710 into 10 to the 6 million years, and it is also found in zircon, pitchblende, uraninite. So these are the common minerals in which we find uranium-235 and Pb-207. Similarly, we have thorium-238 to 232, which converts to Pb-208 through alpha and beta radiations, and its decay constant is 0.000216. Its half-life period is 13.9 into 10 to the 9 years. It is found in columbite, tantalite, monazite. These are the minerals through which we find the presence of thorium and Pb. Similarly, potassium-40 converts into argon-40 having decay constant 0.000252 with age with half-life period that is 11.9 into 10 to the 9 years. The common minerals where potassium argon are found, they are muscovite, biotite, nepheline, sanidine, hornblende, sandstone. So these are the rocks and minerals in which we find these two radioactive elements. Similarly, we have the rubidium strontium. Through beta decay, rubidium-87 gets converted into strontium-87 having decay constant 0.000064 with age half-life period that is 4.7 into 9 years. Common minerals muscovite, biotite, orthoclase, microcline, epidote, glauconite, granites. So these are the rocks and minerals in which we find rubidium and strontium. Similarly, carbon-14 changes to nitrogen-14 through beta decay. Its decay constant is 52.53. Half-life period is 5730 years. And it is found in vegetative matter, animal matter, in sedimentary rocks, groundwater, oceanic water. So carbon-14, nitrogen-14, they are found in these environments, sedimentary rocks, groundwater, vegetative matter, animal matter. Then we have samarium 147, which changes to Nd143, having half-life period 106 into 10 to the power 9 years. So this is the data about the common radioactive elements and their daughters and their half-life periods. And here I have given the example how uranium-238 converts to Pb206. How many alpha and how many beta particles are produced, because of which uranium-238 element is converted into Pb206. So this is the mathematical derivation. We have the mass of uranium-238, which converts into mass of Pb, that is 206, plus 4 into the number of alpha particles produced, plus beta into 0, or number of beta into 0. That gives the mass equation. If we solve it, we find the number of alpha particles produced is 8. 8 alpha particles have been produced through decay of uranium-238 to Pb206. Now if we take into account the atomic number, uranium-92 is converted into Pb82 plus 2 into number of alpha particles, because one alpha particle has a mass which is 4 units and atomic number 2 units. So one loss of one alpha particle results in reduction of mass by 4 units and atomic number by 2 units. So 92 will be equal to 82 plus 2 times the number of alpha particles minus the number of beta particles. So we find that the number of beta particles produced is 6. We solve the equation. 92 is equal to 82 plus 2 into number of alpha particles minus beta particles. So beta particle value becomes 6. So in conversion of uranium-238 to Pb206, there is a loss of 8 alpha particles and 6 beta particles. So this is the way how we calculate the number of alpha particles, beta particles that are being produced in the conversion of uranium to lead. Now let us discuss how rubidium-strontium system is being used for the determination of the age of the rocks. Rubidium-87 decays to strontium-87 by giving a beta radiation or by emission of one electron. 2 half-lives are suggested for the above conversion. They are either 47 billion years or 50 billion years. So rubidium 87 converts to strontium 87 either in 47 billion years or in 50 billion years. Actually, rubidium exists in many types of isotopes, such as rubidium 80. But actually, rubidium exists in many types of isotopes, but only rubidium 87 is found to be radioactive. So, rubidium, if rubidium is having charge 1 or valency 1, which replaces potassium in potassium bearing minerals. It is found to be more compatible with micas because muscovite, biotite, they contain potassium. And that's why rubidium is compatible with muscovite, biotite compared to K feldspar, for which its concentration is high in biotite compared to K feldspar. So, rubidium is more compatible with micas. Similarly, strontium is having valency 2. So, this ion is very small in size and it does not easily substitute for potassium, monovalent potassium in minerals. Rather, it tends to migrate and occurs by replacing calcium from minerals. This is the reason for which rubidium 87 by strontium 87 ratio are used for dating of the rocks becomes less accurate. Why? Some of the strontium are being lost because they replace calcium. Because of this replacement, that the rubidium 87 by strontium 86 ratio which is used for dating of rocks, it becomes less accurate. That's why this ratio, strontium rubidium 87 by strontium 87 ratio, is giving the age of the earth, age of the rocks, which is less accurate. So, strontium 87 is non-radioactive. The ratio of rubidium 87 to strontium 86 and strontium 87 to strontium 86 are used to find out the age of the rocks, because this ratio change due to conversion of rubidium 87 to strontium 87, that is, rubidium 87 by strontium 86 ratio decreases and strontium 87 by strontium 86 ratio increases, because rubidium gets converted into strontium 87. Rubidium 87% decreases, strontium 87% increases. That's why the ratio of rubidium 87 by strontium 86 and strontium 87 by strontium 86 are used to date the rocks and minerals. The initial ratio of rubidium 87, or we can say rubidium 87 by strontium 86, strontium 87 by strontium 86, evolves with time as radiogenic 87 gets converted into strontium 87. I have already discussed that strontium 86 is non-radioactive. That's why if we consider conversion of rubidium 87 to strontium 87, we can take the ratio of rubidium 87 by strontium 86 and compare it with strontium 87 to strontium 86. Then by this we can calculate how much has been the conversion by taking into account the half-life period of rubidium 87 conversion to strontium 87, and by this it is possible to find out the age. If in a rock or mineral there is some initial strontium 87 and then rubidium 87 present changes to strontium 87 during the decay process, it can be referred to the equation 6, where D is equal to D0 plus N into E to the power lambda T minus 1, where D is the total daughter elements, D0 refers to the original daughter element present, N is the parent element, and it is E to the power lambda T minus 1, it is the slope of the line. We have already discussed that this is equation of this refers to an equation of a straight line. Thus D is represented by strontium 87 because rubidium 87 changes to daughter element strontium 87. So D is represented by strontium 87, and this strontium 87 which represents D plus D0. D0 is the original strontium 87 present in the mineral, and some amount of N has been converted into rubidium 87. So the total D is D0 plus D star. D star is equal to N into E to the power lambda T minus 1. This is D star. So this equation can be written with respect to strontium 87, which is the non-radioactive element present in the minerals. If you divide it, the equation becomes, this is the equation. Strontium 87 by strontium 86 is equal to strontium 87 by strontium 86 0 with base 0 plus rubidium 87 by strontium 86 into e to the power lambda T minus 1. It speaks about the fact that rubidium 87 by strontium 86 evolves to strontium 87 by strontium 86, and the rate of increase of strontium 87 by strontium 86 is found to be proportional to rubidium 87, or it is proportional to the number of rubidium 87 converted into strontium 87, or it is proportional to rubidium 87, that is its initial content, because one element of one atom of rubidium 87 when it can be converted into one atom of strontium 87. So the number of atoms of rubidium 87 converted to strontium 87 is proportional to the initial content of rubidium 87 in the rock. The rate of decrease of rubidium 87 by strontium 86 is dependent on the value of decay constant, and there is some initial amount of strontium 87 by strontium 86 in the rock, which is shown as strontium 87 by strontium 86 with base 0. The value of rubidium 87 by strontium 86 to the values of rubidium 87 by strontium 86 and strontium 87 by strontium 86 as found out by mass spectroscopy in rocks and minerals, they are plotted in graphs as shown below. Because we want to find out the age. So by plotting the ratio of rubidium 87 by strontium 86 in the abscissa and strontium 87 by strontium 86 in the ordinate, we put these values and they yield a straight line. The paths along which rubidium 87 by strontium 86 evolves to present composition of strontium 87 by strontium 86 are represented by arrows. If we look at the diagram, so in this axis we have rubidium 87 by strontium 86. In the ordinate we have strontium 87 by strontium 86. So we put the values of these two ratios in the graph, and when they are being plotted, they yield straight lines, and they have been indicated here by arrow. The arrow shows the evolution of rubidium 87 to strontium 87. So as we have discussed that rubidium is more compatible with micas, that's why rubidium concentration is more in biotite compared to K feldspar. And when you talk about the rubidium concentration in biotite, feldspars, rocks, plagioclases, and we plot their values, we get that they evolve in parallel lines. These are the lines. Why these lines are parallel? Because the decay rate is constant. Decay of rubidium 87 to strontium 87, that takes place at a constant rate. That's why rubidium 87 by strontium 86 evolves to strontium 87 by strontium 86 in straight lines as indicated by these arrows. These lines are parallel as their decay constants are same, or decay of rubidium 87 to strontium 87. In each mineral, if each mineral acts as a closed system, the current values of above strontium 87 and strontium 86 ratio from their corresponding rubidium 87 by strontium 86, this is 86, strontium 86 ratio, that is from different minerals and rocks, as each of them have different initial contents of rubidium. So this is the line that indicates the concentration of rubidium 87, and we have the biotite, potassium, K feldspar, rock, plagioclases. So in them the initial content of rubidium 87 is not fixed. That is found to be different as indicated by these initial points. And they have evolved with time. All the rubidiums present in biotite, K feldspar, rock, plagioclases, they evolve with time. That's why their evolution lines are parallel, because they have same decay constants. So they all lie in one straight line. They lie in a straight line which indicates their evolution. But after a particular period of time, if we take all the values of strontium 87 to strontium 86, or if we calculate the age of, if we take into account the strontium 87 by strontium 86 ratio of the rocks and minerals at present time, they lie in one straight line, which is called as these lines are they indicate different time period. This is T for T1 time, this is T2 time, this is T3 time, that means the present time, current composition, present. So these lines are called isochrones or line of same age. So we can, if we plot the data by taking into account the rubidium 87 by strontium 86 with respect to strontium 87 to strontium 86, we get these graphs, and the straight line or the isochrone, which is, let us say this is the isochrone T3 line. This isochrone meets the ordinate at a point which gives the original value of strontium 87 in the rock, that is strontium 87 at the time of the origin of the mineral. So this point, this is the intersection point. So this value is the value of strontium 87 to strontium 86, and it is the initial composition D0. This is D0, daughter element, original daughter element present in the minerals or rocks, and this one gives the D star. So D0 plus D star, they give rise to the total D. So this is total D. And this line that we get by plotting the values of strontium 87 by strontium 86 with respect to rubidium 87 by strontium 86, we get that they lie in one straight line, which is the isochrone, which gives the age of the rock or mineral. And this slope is important, this tan theta, or this is equal to e to the power lambda. This is equal to e to the power lambda t minus 1. As we have seen, this is the tan theta, this is lambda. This is the slope. More the slope, more is the age of the rock. So they lie in one straight line, which gives the isochrone. The slope increases with the age of the mineral or rock. The slope of the best fit line is called the isochrone, or the line of constant age. This line yields the age of the mineral or rock. The y-intercept of the isochrones is the same point, and it provides the value of the initial strontium 87 to strontium 86 in the mineral or rock, or it is the D0. It is same with the theoretical value of the mineral or rock containing no rubidium 87. That means this initial value of strontium 87 by strontium 86 is the characteristic of the source region from which the magma has been derived to produce the rocks and minerals used for the dating. So initial value of strontium 87 by strontium 86 is the characteristics of the source region from which the rock or mineral has been produced. With the increase in slope, the age of the sample increases. Here in the graph we have T3 is the present age, where T1, T2 are the early ages. So T3 is greater than T2, greater than T1. And T0 line is the horizontal line that shows slope tan theta tan 0 is equal to 0, which is the beginning of or the origin of the rock or mineral. That means that age is 0. This method is useful to date the acid and intermediate igneous rocks as they contain K-feldspar and biotite in abundance. So, if you look at this diagram, this line indicates the initial composition of rock or mineral, initial composition of rubidium, and this is the line for age, which age is 0. And this line, this is the isochrone after a lapse of time T1. This line after a lapse of time T2. This line after a lapse of time T3, or this is current age of the rocks and minerals. So this is the slope. More the slope, more is the age. Less the slope, less is the age. And these lines, they are parallel because they show conversion of rubidium 87 to strontium 87. As their concentration is different in different minerals and rocks, these points vary. And they evolve in same rate, that's why these lines are parallel. And the point at which these isochrones they meet the y-axis or the ordinate, that point gives the original value of the strontium 87 present in the rocks and minerals. And this ratio is the characteristics. Strontium 87 by strontium 86 representing the original composition is the representative of the source region from which the magma has been derived and it has undergone cooling to give rise to the rocks and minerals. So this is all about the use of rubidium 87 to strontium 87 in calculation of the age of the rocks and minerals. Next, I will discuss on the closure temperature and blocking temperature and the Concordia-Discordia graph. Thank you all for giving a patient hearing to my talk.